is really similar to how a system with Linux would be structured. Itself, Ironclad inside is nothing but a bunch of services held together. Things like networking unit, mandatory access control, and process unit that we'll talk about later. And it's all held together and accessed when userland requires it via syscalls or whether an input-output event happens. So all of that is really good, but now I'm going to dive a bit into what makes Ironclad special, apart of being written in Ada and being partially formally verified, which we will dive into later as well. One of the things that I wanted Ironclad to be good at, along with the whole thing of being Unix-like, so you can access the whole world of Unix-like applications, is that I wanted a highly secure operating system. And for that, I implemented a feature present in other systems called mandatory access control. Bringing it back to the organization of the operating system, if a program becomes malicious, say by a software vulnerability or it's compromised or otherwise is owned by a bad actor, here represented by Xorg turning evil with the horns and the tail. Given that the kernel is monolithic, whenever a bad program wants to do anything with the system, it will have to interface with the kernel one way or another. If it wants to access disk and corrupt it, or it wants to steal some data from a user that it cannot steal from, it will have to go through the kernel. Mandatory access control basically does it so the kernel keeps a record of what every process can do in what is called the MAC context, or mandatory access control context. And it keeps record of all of this and inherits it from process to process, so that processes can, so you always have a clear path of what a process can and cannot do. In a normal Unix mentality, when a process does something and you specify what it cannot do rather than what it can do, here that's flipped on its head. You have to specify what it can do and everything else is denied. Then the kernel allows different enforcement policies that they are called. Things like killing the offending thread outright or reporting random data. When a violation is detected, it just follows one of these enforcements. In Ada, this looks rather simple. It's just a record with different things that the process can do. Things like scheduling policies that it can do can spawn other processes, along with an enforcement, an array of limits that are the classical U limits that are present in other Unix systems. Things like how much stack a process can allocate, how many file handles it can open, and filters, which are path-based filters, which say what files it can access, what files it cannot access. All of this is inherited from init, which is bit 1 in a classic Unix system. It's all inherited all the way down. The init system is given what is called a 0 MAC context. That means a MAC context with everything allowed, from spawning other processes to accessing every file in the system. And from there, child processes can regulate can further restrict the 0 context and pass it down to further children. This chain, though, only allows for tightening restrictions. It does not allow for permission escalation, which is a big difference compared with schemes like Linux, which allowed certain capabilities for changing MAC at all points. It's a truly restricted system that does a good job at ensuring that malicious processes cannot get their way. Along with that, another interesting thing about Ironclad is scheduling. I wanted with Ironclad to keep it suitable for hard real-time tasks as well as general purpose computing. So Unix, I feel, is not very well suited for this. So I had to add a third identity to the classic Unix scheduling called the thread cluster. In Ironclad, there is 3 scheduling identities that you interface with via syscalls. One is the process, who owns the memory map, threads, open files, the classical Unix notion of process, as well as the thread notion, which in Linux is a bit twisted. You have the both things merging a bit. In here in Ironclad, they are separate identities, truly. The thread, which is the basic unit of execution, has its registers, has its stack, and then there is the thread cluster. The thread cluster can be thought of as a bundle of threads independent of which process they're part of, which are given as a time slice of the total execution time, a cluster time slice of a total time slice that can be configured. And that way we can say that, so we have several clusters with different percentages over a time slice. We can establish real-time guarantees based on that. This, though, given that Ironclad wanted to be a more general purpose operating system, gave the issue that once Ironclad started running things like Xorg, big programs like that, that have a lot of input-output events, this proved not fully suitable, given that these programs, fixed time slices are truly inefficient for them. You may be moving something like a mouse and you need to switch from a process to another fast to keep response times. So to that, it was added the concept of interruptible clusters. Interruptible clusters, instead of using uh, time slices for the whole cluster and switching threads based on the internal policy that is specified for the cluster, use IO events for delimiting which thread is run. That way you can keep a system truly responsive despite having still another cluster with hard real-time guarantees. And with that, another thing that makes Ironclad special is its focus on formal verification. Uh, for Ironclad itself is divided in 3 tiers of such of code. There is architectural code that is very difficult to verify, things like memory map switching, things like register contexts. These things are incredibly hard to delineate in formal verification once you get really deep into them. Then there is code that can be reasonably verified, but has been either verified to a lesser standard because issues that I've mentioned before, or because of time constraints. At the end of the day, everything can be verified to a degree. It's just that with the limited manpower that we have, we kind of have to focus on what we verify the most. And then there are the third option is easy verifiable architecture independent code that we have focused on verifying. Things like cryptography code, things like the mandatory access control code. Those are the things that we have really focused on the project to verify for their security ramifications and the overall ease of it compared with verifying things like table switching code. The verification inside Ironclad looks like your average ADA project using Spark. Has its preconditions, has its postconditions, and here's an example of how the setuid syscall looks. Uh, by establishing things like global in and outs and the precondition postcondition, we can form a net of verified code inside the kernel that allow us to never have to leave verified code for certain operations. Things like user management are fully verified inside the kernel. Things like cryptography routines are fully verified inside the kernel. And these benefits truly extend to userland as well. If we run a userland program which is verified, as we have some of them, a syscall is nothing more than just calling directly into the kernel with a bit of assembly in the middle. So if we have verified code going into verifying syscall, we can achieve a level of security that is not available in the other widespread Unix system. The issue with POSIX, though, is that one of the goals of Ironclad was to be POSIX compatible as much as possible in order to POSIX being a superset or subset, depends on how you define POSIX, I guess, of Unix. The problem is that the global state in Unix is a mess. It's truly horrible. So a function like this, for example, the FD could be one of 30 or 40 types of data types. It could be a socket. It could be blocking or not blocking, which changes things, the side effects taken inside the kernel for those verified functions. And it really is a nightmare to verify. So what we have, so when it comes to the to fighting against the POSIX specification and how it's laid down in terms of insulating global state, what we have done is we have to, what we want to do is we want to strengthen the way that we establish constraints on the userland verifiable code, things like establishing when something is a socket, so we can pass it down to the kernel and make sure that the socket path is taken. Along with that, what's next for Ironclad? Ironclad we recently got to run Xorg on it, which was really exciting. This whole presentation is running inside Ironclad, inside Xorg, which is really cool. We want to work on a kernel profiler because we do have several performance issues right now. A kernel profiler would allow us to see what code paths are being taken more clearly so we could delineate what needs to be optimized and not. We also would like to do a port to RISC-V based boards. Right now, Ironclad runs on x86 systems, and we're working on a ARM port and a Spark port to the Leon 3 series of computers, which are radiation hardened computers. But we would like to expand it to RISC-V based boards given how interesting the RISC-V ecosystem is. And with that, we would like to expand the existing networking support because Ironclad supports networking as it is, but it's really primitive and it's right now constrained on how many network cards we support. We support things like the IPv4 and IPv6, but if you have no network cards to run it with, it's not that good. If you find interesting the project progress or want to check the source code, download it, or see the other materials that we have, I would invite you to check ironclad.cx, where we have all of this and more, along with the current status of formal verification. And alongside with that, I would just like to thank these organizations. The first one being Savannah, financed by the FSF, which allows us to host the code. The Limine bootloader, what that we use for code reference, another code for providing us the tools to formally verify and develop the code itself. And alongside to these people. And thank you for coming to the presentation, and I hope it was interesting.
Thank you.
As I said, let me just give it a go. All of this is being run inside Ironclad. Let me just do a quick new fetch.
If you could increase the font size so that
the font size.
I know
You may be asking me for a bit much. This is ST.
Yeah, I know.
There we go. It will take a bit. There we go. That's why the whole performance thing is. But yeah, that's a new fetch running inside Ironclad, and yeah, pretty cool.
Very, very nice.
Thank you.
So, does anybody have questions here in the room? If not, I have a couple of them.
Yeah.
So I've tested a little bit, as you know, the operating system.
Mm-hmm.
So this is running basically unmodified Xorg, XF3.
This is all software that you could find. The kernel is written from zero with using no code. Yet the userland, we take applications from your usual Linux userland. This is running Xorg, this image that I'm running right now, which is available for building and downloading on the GitHub page of the distribution, which is Gloire. It's running Xorg. The desktop environment is called JWM, Joe's Window Manager, and the terminal emulator is ST. The shell run is bash, and that's just neofetch out of the repository.
Very, very good. Do we have questions online?
Yes. So Frederick is asking what is the coverage you got with Spark in the formal verification?
So for verification, there is a progress report that I update regularly on the Ironclad CX website. Form verification is being carried on as I said, on the most security critical components first. The cryptography code, for example, has been verified to a gold standard that's specified by NatProof. And things like the mandatory access control code have been verified to quite a high standard as well. The rest of userland code that is less architecture dependent has been verified to a mix of lower standards, and architecture dependent code is just all over the place. Some of it is verified, some of it is completely unverified, pure ADA code. It's all reported on the website.
Thank you. I have another question.
Yeah.
Sorry, I don't mean this to be rude.
Yeah.
But why?
Why?
Or when?
No, it's actually a great question. I have been interested in hobbyist operating system development since I was in secondary school. One of my hobbies was just learning just how low you can go on a computer, learning about how all the layers work. I just started learning about how to develop system applications, things like shells. And naturally, I just went on until I got to the operating system level. Since then, I do projects like this, hobbyist operating system, kernels, libcs, stuff that can be used by the community at large and that I enjoy doing.
Mhm. And I have another question. I don't know much about operating systems, but like context switching or syscalls,
Yeah.
those are generally done in assembly, as far as I
Yeah.
know. How do you deal with that? Do you write assembly directly in the ADA code? Or?
Yeah, the operating system kernel Ironclad is made up of something like 95 something percent ADA code, and the other 5% is left for bootstrap code written in assembly, as well as little stubs for things like interrupt routines, this syscall code. All of that has to be in assembly. The CPU has to read it somehow after all.
Mhm. Okay. Do we have more questions online, Javier?
No, no more questions.
Okay. Would you like to show us something else, or?
No, I think it's fine.
Oh.
Well, yeah.
I would like to also mention we have here the maintainer of the Limine bootloader.
Yeah.
You didn't see it boot up, but it's
yeah,
very
it does.
advanced.
It does use Limine. It's a great bootloader that we have used for code reference and to learn how to interface with the lowest levels of the hardware. It's truly a great project. If you guys could check it as well in limine-bootloader.org, it's truly, and it's featured in basically all repositories. It's great.
Thank you. Thank you very much.
Well, thank you so much all for showing up to the talk. That's been really fun.
But if you want to show people like running some applications
Oh
or
yeah,
anything,
well
because
yeah, we can
it
use the time
does
like
run
that.
applications. This is
It
not like
does, yeah.
the iPhone demonstration that is this is actually run.
We have quite a bit few applications supported, some games, some more applications that like text editors and stuff. Guess I might as well just show a solitaire game running inside a fully ADA kernel. And it's all fully functional. It's all buildable and runnable from the GitHub sources that we have. And it's just all the software that we felt like porting to test the kernel and both just have fun with it. After all, it's a hobby project after all. Again, if anyone would like to test this, it's all available on GitHub, downloadable and buildable. And an emulator works, and x86 computer should boot in real hardware as well. It's public for everyone.
And then it takes me to a question.
Yeah.
What software doesn't run?
Well,
where are the limitations, basically?
We normally face more limitations on things like the libc side of things than the kernel. After all, most applications rely on the libc to abstract the operating system functionality, and we got that pretty much nailed down. But things that depend on certain libc routines or that depend on certain behavior only available in Linux libcs, that's truly the problematic parts. Or other group of applications that are really problematic are things like systemd or stuff like that, which rely on strong Linux functionality, things like C groups and stuff, which we have no hope of implementing anytime soon.
Sorry, yes, my bad. Is it possible to run GPS IDE and live an all ADA life?
Well, we have not tried. It's possible to run ADA applications, surely. I just have not tried GPS IDE.
And actually, that takes me to a question. Do you have GNAP GCC ADA support?
Yeah, we do have ADA support. We do not have a runtime library fully nailed down yet. But if what you want is to compile ADA code and you don't mind bringing your own runtime library, like you would compile something with a minimal runtime, that perfectly works. Yeah.
Oh, okay, good.
Yeah, it has GCC port. Let me just do a quick. Well, that's not the dash. There we go. It's just
it's really
no
working.
more GCC. There we go.
Very nice.
Mm.
Oh, and I see we can see here the libc like
Yeah, the
messages.
libc does give issues like that sometimes. So it's like uh, weird behavior. For example, the use of SBRK by GCC is truly a weird use of it. They use it for like error reporting. It's quite fun actually, and that is not implemented inside Gloire. But yeah, it's just normal GCC and modified writing state from the repositories.